Hello, am I audible?
Yes, ma'am.
Okay, just give me 1 minute. Hello, am I audible now? I'm really sorry, there was some issue with the display. I was not able to on this. So, good evening everyone. I'm Shefali Agarwal and I'm a PMRF scholar at IIT Madras. And this is our second TA session on the topic of advanced concrete technology. So, as I discussed before, like how we will go in the complete session is like we will first talk about whatever has been discussed in that week by Professor Manu Sandhanam, and then a brief about all those things, and then we will go to some problem solving session, and at last you can ask your doubts. It can be regarding assignments or the topic which have been taught in the complete week. Okay, so in this week, in first week you might have studied about introduction, cement production, and about cement composition. And in this week we have studied about different codal provisions for cement and introduction to cement chemistry, right? So if I talk about what are the different codal provisions for cements, we have mainly ASTM code, which is dividing ASTM code, which divide our cement in 5 different types: ASTM type 1, 2, 3, 4 and 5, and these are the different compound composition in this different type of cements. So based on this thing we can choose the type of cement which we require based on our construction property. So if we talk about cement 1, that is the most common type of normal pozzolana OPC cement, which we call as, that is a type 1 ASTM 7. So in comparison to that, if we talk about other different type of other type of cements, the type 2 cements have lower C3S composition and lower C3A composition, and in type 3 C3S composition is marginally higher than type 1, and also the fineness value will be more. And in type 4 cement have lower C3S as well as lower C3A. So this is little bit moved. So this is C3A, C2S, C3A, C4AF, and type 4 will have very low C3A composition. Okay, so these are the different type of ASTM classification of cement. So based on these classification, this is the different results which I have got from testing. So if we talk about heat of hydration, the heat of hydration in type 3 cement is more than 1, more than 2. So if you compare the value of C3S, the type 3 cement have maximum C3S and C3A also, then type 1 and then type 2. Type 4 and type 5 have very low, it have a more C3S, but however C3 content is very less, therefore the heat of hydration will be much lower than these 3 type of cements. Okay, and if we talk about compressive strength, so again type 2 and type 4 will have a higher compressive strength after 1 year or something, like in initial stage type 3 cement will have a higher strength. However, when it comes to the longer period, type 2 and type 4 will have a more compressive strength value. Okay, and this is normal OPC cement. After that we have blended cements. So in blended cement we have ASTM give different type of blended cements like slag cement which have 25 to 70% of slag present, then Portland pozzolana cement which have 15 to 40% of pozzolan present like fly ash and all. So what are the benefits of these type of blended cement? It has additional CSH because it is and more pozzolanic reactions, and pore refinement because it will be much finer and having a more surface area, and lastly increased durability. So these are the benefits of adding SCMs or having blended cements with us. Next thing is, what are the default minimum strength requirement according to ASTM C 1157. So these are the again different type of cement which ASTM C1157 talk about, and based on that what should be the strength value on for the for different type of cements. So these things you might have already read in the lecture, so I won't go deep into it. Next thing is about BIS classifications. हम Indian classification, so we use OPC, ordinary Portland cement, which is given by IS 269, and it is further classified into grade of 33, 43 and 53. So generally what grade we are using on site, if anybody know?
'43 and '53.
Yeah. So generally we use 43 and 53 grade of cement on the sites in India. Next is Portland cements or lower cements, that can be the which is mostly used where we have mass concreting like dams and all those area. So in that case we are using IS 12600, and then rapid hardening cement and Portland pozzolana cement, PPC cement and slag cement. So these are the main classification according to Indian standards. So other things we have is EN classification, European classification. So it also divides the cement in 5 type of classification: Portland cement, composite cement, blast furnace, pozzolanic and composite cements. So based on these are the normal cement based on the composition. However, in if we talk about European cements, they are also classified based on their strength value. So here if we talk about 32 N 5 N, that means 32.5 N and 32.5 R. N means normal strength and R means very high early strength. Okay, so these are the three again classification based on the strength value according to European code, or according to Indian code we have 33, 43 and 53, almost similar to these things. So this table will tell about the different strength values at for different type of cements, like based on strength, and this again is telling us the relation between water to cement ratio and compressive strength for different type of strength based cement. Okay, so that was different classification of cement. Next thing, if we talk about cement chemistry, the first thing we talk about in cement chemistry is the hydration of the cement. So whenever a cement is mixed with the water, there is a heat evolution, it is an exothermic reaction as we say. So what exactly is happening in that case is, we have 4 basic compounds of cement, right? C3S, C2S, C3A and C4AF. So in introductory lecture you might have studied about 4 compounds from which cement is made. So from these 4 compounds, what is the different heat of hydration of each compound is given here. Okay, so for pure cement compounds this is the heat of hydration, but when there is a different composition, like if C3S is present 50%, this is 20%, 10% or 5%, something like that, then what is the total heat of hydration of your complete system? So how we are usually calculating those things? We have calorimetry method. So we have 2 type of calorimeters. One is adiabatic calorimeter and other is isothermal calorimeter. So what is the difference between these 2 type of calorimeter? Anybody knows that? Any idea?
Ma'am, isothermal calorimetry used for the calculating the rate of heat of cement, and adiabatic calorimetry used for the calculate the heat evolve of concrete.
Okay, correct.
Okay, correct.
How in measurement method how we will do? If we talk about adiabatic means there is no heat exchange, right? In basic term if we tell. So in adiabatic calorimetry method, there is no heat exchange with the surrounding material. However, in isothermal, what we are doing, we are maintaining a constant temperature. So heat can be exchanged, but temperature will be constant. Okay, so that is the whatever you told is correct only, but that is the what I was asking about, the working principle of both of these things. So if we talk about working principle, in this we are keeping heat, we are maintaining heat, and in this case we are maintaining the temperature. Okay. So since there is no heat loss, this type of calorimetry is used where we want to maintain thermal isolation, or where we have to measure the heat of reactions. Okay, and isothermal is used where we have when we are keeping our temperature constant, and it is used to change measure the changes enthalpy. So usually if we talk about our cement system, when we are making a new cement or any blended cement, then in that case we are using isothermal calorimetry, as you have told that for cements we are using mainly isothermal, and if we talk about concrete we use adiabatic calorimetry. So if we talk about a normal cement OPC, this is a general heat of hydration curve of a normal cement mixed with water. So and this is the total heat generated. So what is happening, initially there is a heat burst, and then we have a slow reaction, this is called as a dormant period, and then this is a main peak, which is the reaction of C3S with water, and then this is due to conversion of AFT to AFM, and then it slow down. Okay, so the main things which take parts in our heating curve is C3S and C3A. So this initial heat burst is mainly due to the reaction of C3A, and this main peak is formed because C3S convert to CSH and calcium hydroxide, CH. So if we, it's written here also, like first is peak 1 is heat of wetting and some early CSH formation. Then we have a dormant period where there is a very slow rate of heat evolution. Then we have a main peak where there is a rapid dissolution of C3S to form CSH and CH, and the formation of ettringite from C3A. Then when a slowdown of hydration process beyond the main peak leads to lower rate of heat evolution. A broader peak of is associated with conversion of ettringite to monosulfate. Okay. Generally this is how a normal peak look like. So what happen if you have more ettringite formation, your second peak will be much higher than this one, and that is not good for our cement properties, like it doesn't give good strength values, because if you are you have more monosulfate in your cement, it is not a good combination. And this is a general total heat evolved. So this is how a normal hydration curves look like. So if you have any doubt, you can ask me, or we will have some questions also on the same thing, then also we can discuss about it. Other thing is how this peaks or total heat will be affected by different factors. So first factor is effect of water cement ratio. So if you are if your water cement ratio increases from 0.4 to 0.6, increasing in water cement ratio will decrease the total heat produced. So like generally if you increase the water content, your heat evolved will be less. Okay. However, other thing is that this okay, that is in next slide also. Other effect is effect of pozzolans or slag. So if I talk about, this is our normal peak, and due to presence of slag there is a little hump at this position. So our new curve will be in this form. So we will have two peaks here, one is primary reaction, one is due to slag. We have a very visible second peak. Okay, And in this case also, if we talk about, this is our control concrete, the sky blue one, and due to the presence of different values of fly ash, this is for fly ash mainly, different fly ash, what is happening, our our total heat is decreasing. There is a decrease in our total heat. It is clear from this case. So this is F type of fly ash. We have added at 30% and 45%. So with addition of fly ash, what is happening? Our formation of CSH is decreasing. So our total heat is also decreasing. Okay. Also, these are the example which are given in your notes for fly ash and slag. You can refer various journal paper which are talking about the recent type of cements like HC3 or silica film or anything you're working on. So this is how, the first test you will do whenever you get a blended cement or any new type of cement. So you need to get the proper you need to get its hydration curve and see how your cement is affecting the hydration process. Why it is required now? If my hydration, this area under this curve will give me the strength value also in the total heat curve. So if my total heat is decreasing, my strength of that cement is also decreasing. Okay. Other thing is, we are talking about this second curve. So this second curve, how this second curve should this second peak should be less than the first major peak. However, in this case, if we have a higher second peak, then how we can decrease that kind of peak is by adding additional gypsum. So if gypsum is added, so what it is doing, it is forming more ettringite and reducing the formation of monosulfate. So if we are reducing the formation of monosulfate, our second peak will also decrease. So it is showing if we are adding so it is actually called as optimum sulfate content. So how to optimize your sulfate content in your cement? So how we can do is by adding extra gypsum, which will decrease the second peak. And when we get this gray type of peak where we have first initial peak as higher than the second peak, that is your optimum content of gypsum. Okay. So this is exactly what is forming in our cement hydration. So if we talk about at initial minutes, there is a little bit formation of calcium hydroxide and CSH, as we have talked about, like in initial initial heat, and then within few hours or days our CSH will keep on increasing. Also our calcium hydroxide will keep on increasing based on your amount of C3S. Okay. Same way your ettringite, your monosulfate will increase and your ettringite will decrease. So ettringite will be converted to monosulfate within many days of time. So these two will be always in reversible thing. Also this C4AFH3, I forgot what it was, so it will also increase. Other thing is when these things are forming, so this is the same graph as this one, how it is affecting the property of your cement. So increasing in CSH and calcium hydroxide will make your system more compact. So what is happening in this case? Your strength is increasing and your porosity will decrease. Same way your permeability will decrease with the formation of more and more CSH gel. So this is a schematic showing how hydration is evolving, and this is the another type of schematic which show at what is happening within few minutes, 10 minutes, 10 hours and all. So this thing, I think sir have only started this work, and he is planning to teach all this thing in week 3. So we will talk about this diagram there itself. Okay. So that's all what you might have studied in week 2, and we will go for some problem solving questions. If you guys have any doubt in the week 2 content, you can ask me now. you can put your question in chat box also. Okay, if there are no doubts, then we will go to some question and answer. So first I will give you a question. It will be mostly MCQ based or one word answer type of questions. So you can just unmute yourself and tell the answer which you think is correct, or you can just put that in the chat box also, the option you think is the correct option. Okay. So the first question is, as per the EN classification for type 3A cement, we can use extenders up to 65%. But the only allowable extender is calcareous fly ash, siliceous fly ash, slag or natural pozzolans. Any idea?
Ma'am, slag.
Slag. Okay.
Okay.
Correct. So it is already given in the slides directly. So the answer is slag. Okay. Technique used to study reaction rates of cement particles: calorimetry, porosimetry, colorimetry, or none of the above. That is a very simple question.
Calorimetry.
Correct. Sorry. A. Correct answer. During cement hydration, the viscoelastic mix transforms to a rigid solid after the final set. Is it a true or false statement? So what? Huh, correct. So what is happening in cement hydration? We have cement plus water. So this mix is actually a viscoelastic mix. I don't know if you guys have read about all this thing. Have you guys, if you have taken this modern construction material, in that course it is clearly shown that how cement paste or concrete is a viscoelastic mix, and it is following that Bingham model and all those things. So and after hydration or after full setting, it will be a rigid solid concrete cement mix, right? So it is a true statement. Next question is, as per EN classification of strength classes for 32.5 N, the compressive strength compliance should be checked at the ages of 2 days, 7 days, 14 days and 28 days. 28 days, okay.
Sir,
Huh? You were saying something? 28 days, 28 days. Okay. So it is actually, if I show you a table, so this is a performance class table. So all type of mixes, whether it's 32 in or everything, will be checked at 28 days window. Along with it, we are talking about for 32.5, which is also checked for the dotted one, which is 7-day thing. So the answer will be 28 days as well as for 7 days. Okay. If we talk about 32.5 hour, then 32.5 hour will be checked for 28 days as well as for 2 days. Okay. So the answer will be B and D. Okay, so the next question is, as proposed by Bogue, approximately half of the total heat of hydration in OPC is evolved in 1 day, between 1 to 3 days, 3 to 7 days or 28 days. More than half of the heat of hydration heat is evolved during how many days? 3 to 7. Okay. Any other person who thinks some other option is correct? Okay. So according to Box, within 1 to 3 days itself, your more than 50% of heat is evolved. Okay. So the answer is between 1 to 3. Is it clear? Okay. So the next question is, in an isothermal calorimeter, the dash is measured. So we talk about two type of calorimeter, adiabatic and isothermal. Huh?
হিট হবে
Heat. Okay.
টেম্পারেচার
Heat or temperature?
টেম্পারেচার
Temperature. You say temperature. So, as I was discussing in isothermal calorimetry, what we are doing? We are keeping our temperature constant, okay, and measuring the heat. Like if you see about our hydration curve, we are measuring the heat evolved, right? So, your temperature is being kept constant, but what is being measured? Your heat is measured, okay. So, it's always your heat which is being measured and your temperature is kept constant, okay. I think you guys have confusion regarding it. So like we were discussing about two type of calorimetry. In adiabatic calorimetry, what we are doing, we are we are protecting it thermally, so there is no heat evolution, okay. In isothermal calorimetry, what we are doing, heat is being evolved, or heat is evolved, and we are measuring that heat, keeping our temperature constant, okay. So when we are keeping a cement paste, we will try to maintain the temperature of our calorimetry. We will try to maintain the temperature of that calorimetry box or something, and we will measure the heat which is being evolved out of it, okay. Is it clear?
ওকে ক্লিয়ার
So in the heat evolution curve for Portland cement, the peak 3 or the shoulder peak after the main peak occurs when C3S forms CSH, C2S forms CH, formation of ettringite from C3A, or conversion of ettringite to monosulfate. So recently only we discussed
D.
D, correct. So our second peak is mainly due to conversion of our ettringite to monosulfate. Okay. So next question is, the strength attainment in a hydrating cementitious system can be judged using the data on heat of wetting, heat rate, cumulative total heat, or dormant period. So strength, if we have these two graphs, one is this one and other is this one. So we were talking about area under the curve, which will be giving us the strength value. So which curve will be used for this strength value? This one or this one? Like A or B?
বি না
Sorry? C? Someone will answer C.
B.
D.
বি বি
Okay. So when we are calculating strength attainment, it will always be from the B. B curve. You're correct. So it is, this B curve is actually from the cumulative total heat. Okay. So answer is C, cumulative total heat. So this first curve is actually a heat rate curve, and the second curve, B curve, is the cumulative total heat curve. Next question is, read the following statements and answer the question. Statement 1 is, reducing the water cement ratio reduces the peak temperature of the hydrating cementitious system, or the dormant period of the hydrating cementitious system can be increased by increasing the water cement ratio. Statement 1 is true and 2 is false, 2 is true and 1 is false, both are true, both are false. What do you think?
Both are true.
Both are true, okay. Any other person who have any opinion? So,
One is false. Sorry. One is false.
yeah.
Yes, they both statement are true.
So you are correct. Actually, statement 2 is true and 1 is false. So if you remember that when we talk about water cement ratio, it will if we are reducing the water cement ratio, your temperature is actually increasing, your total heat generation is increasing. So that's why statement 1 is false. And the dormant period, the waiting period, can be increased by increasing water cement ratio. That is true because it will decrease the temperature. Okay, so the next question is increasing level of fly ash replacement in a Portland cement system results in a lower heat of evolution and reduced dormant period, lower heat of evolution and increased dormant period, enhanced rate of heat evolution and reduced dormant period, enhanced rate of heat evolution and increased dormant period. So we had this graph of fly
B,
ash.
B.
B, okay. So if we are increasing our fly ash content, what is happening? We our heat evolution is decreasing. Also, our dormant period is also increasing. So answer is B. Okay, which of the following statement is or are correct? The progress of cement hydration depends on the rate of nucleation and crystal growth of hydrates. Gel water is the sum of interlayer water and capillary water. The formation of gypsum in the cement influences the hydration rate. Considering the pore solution composition in a blended cement, the unhydrated silica presented in fly ash and slag traps the sodium and potassium ions, reducing the ionic concentration in pore solution. Flash set occurs in presence of large amount of gypsum. So few of the things like about different type of water and all those things you might have not studied as of now. So few option if we talk about A, the progress of cement hydration depend on rate of nucleation and crystal growth of hydrates. That is a correct option, right? In 11th, D you are telling is correct. Okay. Considering the pore
E is false.
sorry, which one?
E1 is false.
E is false, correct, because if we have less gypsum, then only there is a fresh set that we have seen the graph of increasing gypsum content and all. So E is false, D is correct, A is correct. Now come the B and C option. Gel water is the sum of interlayer water and capillary water. So I think in next week you will read about different type of water. Then you will have the CSH, and then there is interlayer water, and you will read about it. So that option is also correct option. Wrong option. Gel water is not sum of interlayer capillary. There is one more thing: interlayer capillary and I forgot about it. But there are three type of water which will come in the gel water concentration. So those three will form gel water. And last option is the form of gypsum in the cement influence the hydration rate. Yeah, so that we have already seen from that curve. The type of gypsum or the concentration of gypsum will influence the hydration rate. So the next question is, reducing the water cement ratio results in reduction in strength of hardened cement paste, reduction in porosity, increase in porosity, or none of the above.
Reduction of porosity.
Correct. So if we are reducing our water cement ratio, what is happening? Our heat evolve will be more. So what will happen? Your strength value will increase and your porosity will decrease. Okay. So next question is, which ASTM cement type is specifically used to reduce the risk of thermal cracking in massive concrete pours? So if I give you an example, if I have to do concreting for dams where we are using mass concreting, and if we are using mass concreting, we need some cement which have lower heat. So what type of ASTM cement have lower heat? 2, 3, 4 or 5?
C.
4. C. Answer 4.
4. Correct. So if we talk about why it have lower heat, because of low content of C3S and C3A. Okay. Which IS code covers Portland Pozzolana cement, PPC cement? IS 269, 8041, 1489, 455.
AIS 269.
IS
PPC 14899.
1489. Correct.
Sorry.
269 is for the ordinary OPC.
Okay.
So 269 is for the OPC, and 8041 is for the rapid hardening, 1489 is for PPC, and 455 is for slag cement. Okay, so same question, but here we are asking about different type of IS and Eurocode. If we are doing mass concreting, which cement is best? 53 grade OPC 42.5 R, IS 12600 or SEM 5. If I see from here itself, IS 12600 is a low heat cement, right? So if we are doing mass concreting and we have option of these type of cement, then we will use IS 12600. Okay. So the next question is, the initial heat burst in my hydration curve is mainly due to Ettringite formation, heat of wetting and some early CSH formation, conversion of AFT to FM, or C2S hydration.
I think B.
Correct. So this initial heat burst, what is happening? There is because of presence of abundant amount of C3A, abundant amount of C3S. There is some initial formation of CSH, and it is also called as heat of wetting. Whenever you are pouring water on anything, there is a initial heating generated, so that is called as heat of wetting. Okay, B is the correct answer. So the instrument used for simulating field condition in heat evolution is adiabatic or isothermal? What do you think? A. Okay, adiabatic.
Adiabatic.
Correct. So since we cannot control our temperature on field, adiabatic is more suitable to simulate the field condition. Why does an adiabatic calorimeter show higher temperature rise than isothermal calorimeter? It accounts for heat loss, it does not allow heat loss to surrounding, it has faster hydration, or it uses higher water cement ratio.
B.
Correct. So simple answer. Okay. So this is a little bit of a calculation type of question. If a cement contains 55% of C3S, 25% of C2S, 10% of C3A and 8% of C4AF, estimate the theoretical heat of hydration. So if you remember, we have this table. Can you calculate the total heat of hydration? You can take a few minutes and calculate it. Anybody who have tried it, or you're getting the formula or something? So simply what we are doing, first heat of hydration for first compound, that is 55% means 0.55. Same way this multiplied by C2S is 0.25 and this multiplied by 0.10 and this multiplied by 0.08. So this is the formula which you will be using, 461. Okay, good. It will be approximately 500 to 510 joules per gram. Just try it once. Okay, I will also try. $260.
461.3.
Sorry, it's 461.32. So you are correct only. So I will correct it and then update the PPT. So it will be approximately 462 joules per gram. Approximately equal to 462. Okay. So the last question for today's session is, if gypsum is removed from cement, peak 2 will be, it will disappear, it will appear earlier and will be more sharper, it will shift to later time or remain unchanged?
B.
P, correct. So if you remember the gypsum diagram, if there is less gypsum, your second peak will be more earlier and more sharper. Okay, so that's all for this week 2. If you have any doubts, you can contact me on my mail IDs. These are my mail IDs. And also, if you have any doubt in this week 2 session or assignments or anything, you can ask me now. Somebody raised hand. Or you can unmute yourself and ask.
And I have two questions. One question is how supplementary cementitious material like fly ash and slag perform better against alkali environment or alkali silica reaction, and what is the mechanism? And second question is how much amount of calcium hydroxide produced by the cement?
In case of SCM.
No, the second question is for ordinary Portland cement only.
Okay. So when you have C3S, your C3S plus water will actually form CSH and calcium hydroxide. So you are asking how calcium hydroxide is formed, or what you were asking?
I'm asking supplementary cementitious material like fly ash or slag perform better against alkali silica reaction. How?
How
And
is
what
it?
is the mechanism?
Can you mute yourself? So you are asking about alkali silica reaction with the in the presence of SCM, right?
G.
So if we talk about alkali silica reaction, it is mainly due to the between aggregate and your cement material, right? So in case of your SCM, you have a lower content of C3S. So that means you have much lower silicates present in your concrete. So if you have a lower silicate present in your concrete, the reaction of this alkali silica will be lesser as compared to your OPC. Your OPC will have a more silicates. Does that clear your doubt?
Yes, ma'am.
And your second doubt was?
My second doubt is how much amount of calcium hydroxide produced by 100 gram of cement? How much amount of calcium hydroxide produced by OPC?
How much amount of calcium hydroxide? That I also don't know how to do that calculation as of now. I have to go check it. Maybe in next class I can tell you about it.
Okay, ma'am. Okay. Thank you.
Any other doubt? If there are no doubts, then we will close the class for today. Thank you for joining. You can leave the meeting.
Thank you.
Thank you.
Thank you.